Today, on December 19th, 2025, at exactly 0240 Coordinated Universal Time, Earth screamed. Not metaphorically, not in some poetic sense. A monitoring station in Siberia registered a 25 Hz spike in our planet's electromagnetic field, isolated and precise as a scalpel cut, arriving 3 hours before an interstellar object completed its flyby. This wasn't thunder. This wasn't human interference. And it wasn't the first time. Just 11 days earlier, the same frequency appeared before Japan's devastating magnitude 7.6 earthquake. 2 events, same signal, except this time there's another actor at play. So here's what keeps scientists awake at night. Was 3i Atlas just passing through? Or did something answer when it knocked? Stay with me, because what will happen next might challenge everything we thought we knew about what's really out there. Part 1. The moment Earth lit up. At exactly 0240 Coordinated Universal Time on December 19th, 2025, something happened that nobody predicted. A frequency monitor in Siberia registered a signal that shouldn't have been there. The timestamp matters because this wasn't the moment when 3i Atlas made its closest pass to our planet. This was 3 hours and 20 minutes before perigee. The interstellar visitor was still approaching, still inbound, and Earth was already responding. The signal appeared at 25 Hz, not 24, not 26, 25. A single, isolated spike on the spectrogram, narrow as a laser cut, appearing in the Schumann resonance data like someone had just pressed a key on a piano that had been silent for months. What makes this unsettling isn't the frequency itself, it's the precision. Natural electromagnetic phenomena tend to sprawl across the spectrum. Lightning creates a wash of frequencies, a smear of energy from near zero, all the way up into the kilohertz range. Geomagnetic storms produce broadband chaos, entire sections of the electromagnetic spectrum lighting up like a Christmas tree having a seizure. This did none of that. This was a line. A single, clean, vertical line at 25 Hz, holding steady for minutes while the world spun beneath an interstellar object that had travelled for millions of years just to skim past us at 1.8 astronomical units. The people who noticed it first weren't amateur enthusiasts scrolling through data for fun. These were observers who'd been watching Schumann resonance monitors for years, people who knew what lightning looked like, what instrument noise looked like, what the baseline hum of Earth's electromagnetic environment was supposed to do on a quiet December morning. They knew what they were looking at wasn't supposed to be there. Stefan Burns posted about it publicly, and within hours, the signal had a nickname, a timestamp, and a growing sense among those paying attention that something had just happened that nobody could quite explain. The confusion wasn't panic. It was the specific kind of unease you feel when pattern recognition fires in your brain and you can't shut it off. Why this frequency? Why this exact timing? Why now, during the first confirmed interstellar object flyby since Borisov? During a moment when Earth and this ancient traveller were briefly sharing the same cosmic neighbourhood. You want to dismiss it. You want to say it's nothing. But 25 Hz isn't nothing. It's a loaded number. It's a frequency that keeps showing up in datasets that makes scientists uncomfortable, and it was back, right on schedule, 3 hours and 20 minutes before closest approach. If this was a warning, we got it early. If it was a signal, we weren't listening for it. And if it was just noise, well, noise doesn't usually arrive with that kind of timing. Part 2. Why 25 Hz is a loaded number. Schumann resonances are supposed to be simple. They're the electromagnetic hum of Earth's atmosphere, the resonant frequencies that exist because we live inside a spherical cavity bounded by the ground below and the ionosphere above. Lightning strikes excite this cavity thousands of times per second, and the cavity rings at its natural frequencies. The fundamental mode sits around 7.83 Hz. The second harmonic is at 14.3. The third is at 20.8. These are the frequencies we expect. These are the frequencies that show up day after day in monitoring stations around the world. 25 Hz is not one of those frequencies. It sits just above the third harmonic, in a region of the spectrum where Schumann resonances aren't supposed to dominate. But it's not random, it's not arbitrary. 25 Hz falls squarely inside a frequency window that has haunted seismologists and geophysicists for decades. The 15 to 35 Hz band is where earthquake precursors live, or at least where they're claimed to live. This is the frequency range that shows up in controversial datasets, in studies that get published and then quietly ignored, in research that suggests Earth's crust might be screaming at us before it breaks. The idea is simple, even if the mechanism isn't. When rock is under stress, when tectonic plates are locked and straining against each other, the piezoelectric effect can generate electromagnetic signals. Quartz crystals in granite, subjected to enormous pressure, produce electrical charges. These charges, in theory, can propagate through the crust and into the atmosphere, creating detectable electromagnetic anomalies before the rock finally gives way. 24 to 26 Hz keeps appearing in these studies. Not always, not reliably, but often enough that it earned the nickname key frequency among researchers who take this work seriously. The problem is that nobody can predict earthquakes. The precursor hypothesis has been tested, debated, and largely sidelined because correlation isn't causation, and false positives are unforgivable in disaster science. But the frequency keeps showing up. It appeared in datasets before major quakes. It appeared in lab experiments where rock samples were crushed under hydraulic pressure. And now it was appearing in Schumann resonance data. Narrow and isolated, 3 hours before an interstellar object made its closest pass. Lightning creates broad, messy signals. A lightning strike dumps energy across a wide range of frequencies simultaneously, exciting multiple harmonics at once. You see this on spectrograms as vertical bands, wide smears of colour that light up the entire lower end of the spectrum. What you don't see is a single frequency lighting up by itself, holding steady, refusing to spread. That's what narrow band means. That's what makes this signal strange. It implies a source that's coherent, that's oscillating at a specific frequency, without the chaos that normally accompanies natural electromagnetic phenomena. Skeptics will tell you correlation isn't prediction, and they're right. Seeing 25 Hz on a spectrogram doesn't mean an earthquake is coming. It never has, not reliably. But Japan might make you think twice about dismissing it entirely, because this frequency didn't appear in isolation. It had shown up before, just days earlier, in a context that nobody wanted to talk about once the dust settled. Part 3. The Japan Precedent. Nobody wanted to talk about. December 8th, 2025. Magnitude 7.6. The earthquake struck off the coast of Japan with enough force to rattle buildings and trigger tsunami warnings across the region. It was significant. It was damaging. And it was preceded by something that made a small number of observers very, very uncomfortable. Days before the quake, the same Tomsk monitoring station that would later detect the 3I Atlas anomaly registered a Schumann resonance disturbance. The frequency profile looked similar. The timing was eerie, and then, when the earthquake happened, the conversation quietly faded. This wasn't the first time anomalies had been reported before major seismic events. It wasn't even the first time this particular frequency range had shown up. But it was the first significant Schumann anomaly in months, appearing right before one of the largest earthquakes of the year, in a region that's perpetually on edge. The pattern was uncomfortable because patterns are supposed to mean something. We're trained to see cause and effect, to assume that when A precedes B, there might be a relationship worth investigating. Precursor science is controversial because it promises something it can't deliver. It suggests that Earth telegraphs its intentions before disaster strikes, that there are measurable signals we could use to save lives if only we knew how to read them. But earthquake prediction has a graveyard of failed attempts. Scientists have tried everything from radon gas measurements to animal behaviour studies to electromagnetic monitoring, and none of it has produced a reliable warning system. So when anomalies appear before earthquakes, the professional response is usually to shrug and move on. Post hoc analysis is easy. Prediction is impossible, except researchers don't claim exact prediction. They talk about stress windows, about elevated risk states, about statistical clustering that might give you a few days of heightened awareness instead of nothing at all. The idea isn't to predict the exact moment a fault will rupture. The idea is to recognise when the crust is in a state where rupture becomes more likely. Think of it like weather forecasting. You can't predict the exact moment lightning will strike, but you can recognise atmospheric conditions that make thunderstorms probable. Comparing statistical clustering versus randomness is where the debate gets heated. If Schumann anomalies appeared randomly throughout the year, you'd expect them to occasionally precede earthquakes just by chance. But if they cluster in time windows before seismic events more often than randomness would predict, that's worth investigating. The Japan event wasn't proof of anything. It was a data point. One more entry in a ledger that's been accumulating uncomfortable correlations for decades. And now it had happened again, during an interstellar flyby. The coincidence was starting to feel less like coincidence, and more like a pattern nobody wanted to acknowledge. Because if you admit the pattern might be real, you have to start asking how it could possibly work, and that question leads to places most scientists would rather not go. Part 4. Tomsk, the T antenna, and what this sensor is actually good at. The Tomsk Space Observing System isn't some backyard hobbyist project. It's a research-grade monitoring station operated by the Russian Academy of Sciences, specifically designed to measure vertical electric field variations in the extremely low frequency range. The sensor array uses what's called a T antenna configuration, essentially a pair of metal plates separated vertically to detect changes in the atmospheric electric field. It samples continuously from 0 to 40 Hz, recording the electromagnetic heartbeat of the planet in real time. The data gets published online, accessible to anyone with an internet connection, and enough curiosity to scroll through spectrograms. This openness is both a strength and a vulnerability. It means independent researchers can verify observations and catch anomalies that might otherwise go unnoticed. It also means every blip, every artifact, every questionable signal gets scrutinized by people with varying levels of expertise and varying degrees of skepticism. Tomsk has weaknesses. Every sensor does. Wind can create vibrations in the antenna structure. Nearby electrical equipment can introduce interference. Temperature fluctuations can affect the electronics. These sources of noise are well documented, and experienced observers know what they look like on a spectrogram. Microphonic noise from wind typically creates broadband hash across multiple frequencies, a fuzzy smear that rises and falls with gusts. Electrical interference from power lines shows up as sharp harmonics at 50 or 60 Hz, and their multiples, depending on which power standard the local grid uses. The 25 Hz signal didn't look like either of those things. It appeared as a discrete, narrow spike, isolated from the usual Schumann harmonics, without the characteristic spread or harmonic structure you'd expect from common sources of contamination. Critics will default to instrument artifact anyway, because that's the safest assumption when you see something unusual. Most anomalies are instrument artifacts. Most unexplained signals turn out to have mundane explanations once you dig deep enough. But morphology matters. Signal shape matters. If you've spent years watching Schumann spectrograms, you develop an intuition for what belongs and what doesn't. You learn to distinguish between the organic chaos of natural phenomena and the artificial precision of human-made interference. The 25 Hz signal had characteristics that didn't fit neatly into either category. It was too clean to be natural, too isolated to be typical interference, and too well timed to dismiss as random chance. This isn't about belief. This is about signal processing, about pattern recognition, about asking whether what we're seeing matches known categories of electromagnetic activity or falls outside them. Even if the signal was real, even if it wasn't an artifact, that just raises the next question. What could cause an isolated 25 Hz spike in Earth's Schumann resonances during an interstellar flyby? What mechanism could possibly link those two events? And that's where the conversation splits into two very different paths. Part 5. Coincidence versus coupling. The first fork in the road. There are only two options here, and neither one is comfortable. Option A is pure coincidence. 3i Atlas flew past Earth at 1.8 astronomical units, while sensors happened to detect an electromagnetic anomaly at 25 Hz, and these two events are completely unrelated. This is the statistically tempting explanation. Space is big. Things happen all the time. Correlation without causation is the null hypothesis, the default position any rational person should take when confronted with unlikely timing. Coincidences happen. They happen more often than we expect because we're bad at intuiting probability. We see patterns everywhere, connecting dots that aren't actually connected because our brains evolved to detect predators in the grass, not to perform rigorous statistical analysis. The interstellar object passed by. The signal appeared. Maybe those are just two independent events that happen to overlap in time, and we're committing the cardinal sin of post hoc reasoning by assuming one caused the other. Option B is coupling or triggering. Something about the flyby, something about the interaction between this ancient chunk of rock and ice and Earth's electromagnetic environment produced a measurable effect, not through gravity, not through direct physical force, but through some subtler mechanism that we don't fully understand yet. This option doesn't require intelligence, it doesn't require intent, it just requires that Earth is a complex, interconnected system capable of responding to perturbations in ways we haven't mapped yet. The difference between cause and trigger is critical here. A cause produces an effect through direct energy transfer. You push something, it moves. Trigger releases energy that's already stored in a system. You flip a light switch, and a power plant miles away does all the work. Triggering is about timing, about phase relationships, about hitting a system at exactly the right moment to tip it from one state to another. Metastable systems are everywhere in nature. An avalanche sits on a mountainside, ready to collapse, waiting for one more snowflake to break the balance. An earthquake waits for decades while stress accumulates in the crust, and then a tiny additional strain, maybe from a distant seismic wave or a change in groundwater pressure, provides the final push. These systems don't need large amounts of energy to fail. They need the right perturbation at the right time. Earthquakes have been triggered by surprisingly small influences, the passage of seismic waves from distant quakes, reservoir filling, wastewater injection, tidal stresses from the moon and sun, even though those gravitational effects are minuscule compared to the forces already present in the crust. What matters isn't the strength of the trigger. What matters is whether the system is already at the edge, already primed, already waiting for something to push it over. Timing matters more than energy. This is the part that breaks people's intuition. We expect big effects to have big causes, but that's not how nonlinear systems work. A system on the edge of instability can respond dramatically to tiny inputs, not because the input is powerful, but because the system is ready. And if Earth's electromagnetic environment was already in some kind of elevated or resonant state when 3I Atlas passed by, maybe the timing of that passage mattered more than the distance or the gravitational pull. Neither option is comfortable. Coincidence feels unsatisfying because the timing is too good, too precise. Coupling feels unsettling because it implies mechanisms we don't understand, connections between cosmic events and planetary phenomena that aren't supposed to exist. You want there to be a third option, something clean and obvious that resolves the mystery without requiring you to pick a side, but there isn't one. Either this meant something, or it didn't, and if it meant something, we need to figure out how it could possibly work. Part 6. Why gravity alone doesn't save the skeptics. The first thing skeptics reach for is distance. 3I Atlas passed Earth at roughly 1.8 astronomical units. That's about 270 million kilometres, roughly 1.7 times the distance from Earth to the Sun. At that range, the gravitational influence of the object on our planet is negligible. Not small, negligible. The Moon exerts tidal forces on Earth that are 6 orders of magnitude stronger. The Sun's gravitational pull is 3 orders of magnitude stronger than that. An interstellar object at nearly 2 astronomical units might as well not exist from a gravitational perspective. Tidal forces drop off with the cube of distance. Triple the distance, and the tidal effect decreases by a factor of 27. At 1.8 astronomical units, 3I Atlas was exerting gravitational forces on Earth that wouldn't move a grain of sand, wouldn't raise the ocean by a nanometer, wouldn't stress a fault line by any measurable amount. This is why gravitational skeptics feel confident. The math is simple. The forces are laughably small. Case closed. Except gravity isn't the only game in town. Interstellar objects don't travel through empty space. They travel through the solar wind, through magnetic field lines, through plasma environments that extend far beyond the gravitational reach of planets. 3I Atlas wasn't just a rock flying past Earth. It was a charged body moving through a magnetized medium, trailing a plasma wake, interacting with the Sun's magnetic field and Earth's magnetosphere in ways that gravity alone can't describe. Charged particle interactions can occur at enormous distances. When comets approach the Sun, their plasma tails stretch for millions of kilometres, far beyond the point where gravitational forces matter. These tails are shaped by the solar wind and the interplanetary magnetic field, creating structures that respond to electromagnetic forces rather than gravity. If 3I Atlas was outgassing, even slightly, it was creating a localized disturbance in the plasma environment around it. Earth sits inside the solar wind, inside the sun's extended magnetic field, inside a dynamic electromagnetic environment that's constantly changing. The magnetosphere shields us from most of this, but it's not a perfect barrier. Charged particles leak through the cusps at the poles. Magnetic field lines connect our atmosphere to the solar wind. Alpha waves propagate along these field lines, carrying energy from one region to another at speeds that have nothing to do with the motion of the plasma itself. Non-gravitational interactions are speculative, but they're not baseless. We know that electromagnetic coupling occurs between bodies in space. We know that plasma environments can mediate interactions over vast distances. What we don't know is whether an interstellar object at 1.8 astronomical units could produce a detectable electromagnetic signature on Earth's surface. The energy budget doesn't make sense through any conventional pathway. But conventional pathways aren't the only ones. Resonance doesn't need force, it needs timing. A child on a swing doesn't need a strong push to go higher. They need a push at exactly the right moment, synchronized with the natural frequency of the swing. Give 100 small pushes at random times and nothing happens. Give one small push at the right time and the amplitude grows. This is how resonance systems work. They amplify inputs that match their natural frequencies and ignore everything else. If Earth's electromagnetic environment is a resonant cavity, and if something about the flyby provided a stimulus at the right frequency, you wouldn't need large amounts of energy. You'd need coherence. You'd need timing. You'd need a perturbation that matched Earth's natural oscillation modes closely enough to excite them. And maybe, just maybe, that's what happened at 0240 UTC. Not because 3I Atlas pushed Earth, because it rang a bell that was already humming. Part 7. Resonant cavities, high Q events, and why isolation matters. Resonance is everywhere once you know how to look for it. A wine glass shatters when you hit the right note. A bridge collapses when soldiers march in step at its natural frequency. An opera singer can shatter crystal without touching it, using nothing but sound waves that match the glass's resonant frequency, precisely enough to build amplitude until the structure fails. These aren't magic tricks. They're demonstrations of how resonance systems respond to coherent inputs. Earth is a resonant cavity. The space between the ground and the ionosphere forms a spherical shell that traps electromagnetic waves, allowing certain frequencies to persist while others cancel out through destructive interference. The fundamental resonance is 7.83 Hz because that's the frequency whose wavelength fits neatly around Earth's circumference. Higher harmonics exist at integer multiples, creating a ladder of frequencies that the planet naturally supports. High Q means high quality factor, a measure of how well a resonance system maintains oscillations. A high Q system rings like a tuning fork, oscillating at its natural frequency for a long time with minimal damping. A low Q system is like a sandbag, absorbing energy and stopping quickly. Earth's Schumann resonances have relatively high Q, which is why we can detect them continuously, despite lightning being sporadic and localized. The cavity holds onto electromagnetic energy, letting it slosh around for seconds or minutes before dissipating. Isolation matters more than strength in high Q systems. Broadband noise, the kind of electromagnetic chaos produced by lightning storms or solar flares, doesn't excite resonances efficiently because the energy is spread across too many frequencies. Most of it misses the resonant peaks, dumping into modes that damp out immediately. But a narrow band signal, a coherent oscillation at exactly the right frequency, can build amplitude even if it starts weak. The cavity accepts that energy, stores it, amplifies it through constructive interference. Engineered resonance systems exploit this principle ruthlessly. Radio transmitters use resonance circuits to amplify specific frequencies while rejecting everything else. Musical instruments use resonant cavities to make weak vibrations audible. Particle accelerators use resonant cavities to accelerate charged particles to near light speed with relatively modest amounts of input, power, because the cavities store energy and release it in phase with the particle's motion. Broadband noise behaves differently. It's like trying to push a swing at random times. Most of your pushes work against the motion, cancelling out the energy you put in. Only occasionally do you happen to push at the right moment, and even then the effect is weak because the next push might undo it. This is why lightning, despite being energetic and frequent, doesn't dominate Schumann resonances as much as you'd expect. The energy is there, but it's incoherent, scattered across frequencies, unable to build amplitude in any single mode. Earth might ring under certain conditions that we haven't mapped yet. The ionosphere isn't uniform. Solar activity changes its height and conductivity. Geomagnetic storms create irregularities. The entire cavity is dynamic, constantly shifting in ways that affect its resonant properties. Maybe there are times when the cavity becomes unusually receptive to certain frequencies, when the Q factor increases, when isolation from background noise improves, and maybe, just maybe, December 19th was one of those times. This is speculative. It has to be labelled as speculative because we don't have measurements of the ionosphere's state during the flyby. We don't have baseline data on how often 25 Hz spikes occur randomly, and we don't have a proven mechanism linking interstellar flybys to electromagnetic resonances. But speculation isn't worthless. It's the first step in forming testable hypotheses, and some researchers find this idea genuinely exciting because it suggests Earth is more dynamic, more responsive, more alive in an electromagnetic sense than we usually assume. What if Earth was already tuned? What if the cavity was already primed, already oscillating at modes we don't monitor closely, and the flyby provided just enough coherent stimulus to tip one of those oscillations into visibility? That's not a claim. That's a question. And it's a question that leads directly to the most unsettling hypothesis of all. Part 8. The trigger. Hypothesis. You don't need energy, just timing. Threshold systems are brittle. They sit at the edge of instability, balanced between one state and another, waiting for the smallest perturbation to push them over. An earthquake is a threshold event. Stress accumulates in the crust for decades, building slowly as tectonic plates grind past each other, and then one day the rock fails. The failure happens in seconds, releasing energy that took decades to store. The trigger for that failure might be tiny compared to the forces already present. Other examples are everywhere. A blackout can cascade through a power grid when one transmission line fails, redistributing load to other lines that then fail in turn, creating a domino effect that shuts down an entire region. An avalanche waits on a mountainside until one skier crosses at the wrong angle, breaking the friction that held the snowpack in place. These aren't events where the trigger provides most of the energy. These are events where the trigger unlocks energy that was already there. Phase locking is how oscillating systems synchronize with each other. If you put two metronomes on a shared platform, they'll gradually sync up, ticking in unison even though they started at different times. The platform couples them weakly, allowing small vibrations from one to influence the other. Eventually, the influence becomes strong enough that both metronomes lock into phase, oscillating together. No external force is needed. The coupling does all the work. The flyby could have acted as a timing perturbation, not a force, not an energy source, just a stimulus that arrived at a moment when Earth's electromagnetic environment was receptive. Maybe the cavity was already oscillating at 25 Hz, too weakly to be detected, and the passage of 3i Atlas provided a coherent input that reinforced that oscillation. Maybe the object's plasma wake disturbed the solar wind in a way that propagated to Earth's magnetosphere, creating a momentary change in field line tension that coupled into the ionosphere. This is hypothesis, not proof. It's important to keep saying that because speculation without caveats becomes pseudoscience. We don't know that this happened. We don't even know if it's possible. What we have is a correlation, a plausible mechanism, and a growing sense that dismissing it without investigation might be premature. But hypothesis is how science progresses. You notice something odd, you propose an explanation, you test it. We're still at step 1. Timing alignment is unsettling because it implies coherence. Random events don't align. They happen whenever they happen, and coincidences occur, but they're rare. When you see repeated timing correlations, when signals appear at specific moments relative to other events, your brain starts looking for causal connections. That's not irrational. That's pattern recognition doing its job. The question is whether the pattern is real, or whether we're seeing faces in clouds. Lead-lag relationships would help resolve this. If Schumann anomalies consistently appeared before interstellar flybys, that would suggest precognition, which is absurd. If they consistently appeared after flybys, that would suggest aftermath effects. If they appear during flybys, that suggests real-time coupling. The Japan earthquake anomaly appeared before the quake, which fits the precursor hypothesis but doesn't tell us whether the flyby was involved. The 3I Atlas anomaly appeared before closest approach, which doesn't fit a simple aftermath model. This doesn't require intelligence. That's critical to emphasize. A coupling mechanism, if it exists, could be purely physical. Electromagnetic systems respond to stimuli according to Maxwell's equations, not according to intent. There's no need to invoke consciousness, or purpose, or design. The universe is full of systems that interact through physical laws we understand. The question is only whether we've identified all the relevant interactions, or whether there are couplings we've overlooked. Skeptics still struggle with it, and they should. Extraordinary claims require extraordinary evidence, and we don't have that yet. What we have is intriguing data, uncomfortable timing, and a hypothesis that's barely formed. But struggling with an idea isn't the same as dismissing it. Science advances when we take uncomfortable observations seriously enough to investigate them properly. And this observation is deeply, profoundly uncomfortable. Because intelligence is the next thought everyone has, even if they don't say it out loud, even if they know it's probably not true. Part 9, Artificial versus Natural, Why the Signal Feels Uncomfortable. Artificial means designed. It means purpose. It means someone or something created a signal with specific characteristics for specific reasons. When engineers talk about artificial signals, they mean transmissions with structure, with modulation, with information content, a carrier wave at a specific frequency, a pulse pattern, a bandwidth that's narrower than nature usually produces. These are the hallmarks of technology, the signatures that let SETI researchers distinguish between cosmic noise and potential alien transmissions. Narrowband signals raise eyebrows because nature doesn't usually do narrowband. Natural processes are messy. Lightning produces broadband chaos. Pulsars produce short pulses with wide spectral content. Even masers, those rare cosmic microwave amplifiers, have finite bandwidth. When you see a signal that's confined to a tiny slice of frequency space, your first thought is that something is generating it deliberately, focusing energy into a specific mode for reasons that aren't random. Human ELF emitters exist. Extremely low-frequency transmitters are used for submarine communication because long wavelengths penetrate seawater. These systems operate at frequencies between 3 and 30 Hz, exactly the range where Schumann resonances live. The problem is that known ELF transmitters don't match this timing. Submarine communication systems run continuously or on predictable schedules, not for brief periods at 0240 UTC during an interstellar flyby. None of the known sources fit. This isn't a submarine transmission, it's not a power line harmonic, it's not an atmospheric phenomenon with an obvious terrestrial explanation. That leaves you with 3 options. It's an unknown natural process that we haven't characterized yet. It's an instrument artifact that looks natural but isn't. Or it's something artificial that we don't have context for. That third option is where the conversation gets uncomfortable fast. There's no evidence for intent. That needs to be stated clearly and repeatedly. Seeing an anomalous signal doesn't mean someone sent it. Seeing unusual timing doesn't mean something is trying to communicate. The history of science is full of mysterious signals that turned out to be natural. Pulsars were briefly called LGM signals, for little green men, until we understood they were rotating neutron stars. Fast radio bursts were thought to be artificial, until we found enough of them to characterize them as astrophysical phenomena. Human pattern bias is real and powerful. We see faces in clouds, hear voices in static, detect messages in randomness, because our brains are prediction machines optimized for false positives. Missing a real pattern could get you killed in the ancestral environment. Seeing a fake pattern costs you nothing. So we evolved to see patterns everywhere, even when they're not there. This is why scientists are trained to be skeptical, to demand reproducibility, to resist the temptation to jump to exciting conclusions based on single observations. Scientists avoid this topic publicly because it's career poison. Suggesting that an anomalous signal might be artificial, even as a hypothesis worth testing, opens you to accusations of pseudoscience, attention-seeking, and conspiracy thinking. The professional cost is high, and the evidence is never strong enough to justify it. So people stay quiet. They discuss it in private emails, in conference hallway conversations, but never in papers or public statements. Unexplained doesn't equal alien. This is the mantra that keeps everyone sane. Most unexplained things turn out to be explained once you gather more data. Most anomalies are artifacts. Most correlations are coincidences. The null hypothesis is boring and usually correct. Entertaining alternative explanations doesn't mean accepting them. It means staying intellectually honest about what you do and don't know. But unexplained also doesn't equal dismissed. Ignoring anomalies because they're uncomfortable is how you miss real discoveries. Continental drift was dismissed for decades. Ball lightning was considered folklore. Meteorites were thought to be impossible because rocks don't fall from the sky. Science has a graveyard of phenomena that were rejected because they didn't fit existing models, and later turned out to be real. The lesson isn't to believe every anomaly. The lesson is to investigate them properly instead of assuming they'll go away if you ignore them long enough. The pattern keeps returning, and that's what makes it stick in your mind. Japan, 3-eye atlas, 25 Hz appearing at times when something significant is happening. Maybe it's coincidence, maybe it's confirmation bias, but maybe it's worth watching the data more carefully, building better models, asking whether we're missing something about how Earth responds to electromagnetic stimuli. And if we're wrong, we've wasted some time, but if we're right, we've missed decades of signals because we were too uncomfortable to look. Part 10. The pattern problem, when correlations refuse to die. Japan and 3-eye atlas together create a sample size of 2. That's not enough to prove anything. That's barely enough to justify writing about. But it's enough to make you pause, enough to make you wonder whether there's a third event waiting to be found in old data, whether someone should go back through Schumann records and seismic catalogues and interstellar object flybys to see if this has happened before without anyone noticing. Clustering versus randomness is a statistical question with no clean answer when your sample size is small. If you have 2 events that coincide with unusual timing, you can calculate the probability that both happened by chance. But that calculation depends on your assumptions about base rates, about how often each type of event occurs independently, about whether you're cherry-picking examples. Get the assumptions wrong, and you can make anything look significant or anything look random. Humans oversee patterns. We're wired for it. Show us 3 dots in a row, and we'll see a line even if the dots were placed randomly. Tell us to watch for correlations, and we'll find them everywhere because we're selectively attending to hits while ignoring misses. This is why anecdotal evidence is dangerous. This is why scientists demand controlled experiments instead of trusting their intuition about what goes together. But ignoring anomalies stalls progress. If you reflexively dismiss every unexpected observation, you never investigate anything. Discovery requires noticing things that don't fit, taking them seriously enough to gather more data, building explanations that account for what you've seen. The balance is delicate. Be too skeptical, and you miss real phenomena. Be too credulous, and you waste resources chasing phantoms. Historical cases exist where anomalies mattered. The orbit of Mercury didn't fit Newtonian predictions, and that anomaly eventually led to general relativity. The spectrum of black body radiation didn't match classical physics, and that led to quantum mechanics. Cosmic microwave background radiation was detected as annoying noise in a radio antenna, and it became the smoking gun for the Big Bang. These weren't obvious at the time. They were weird little mismatches that people took seriously instead of explaining away. The status here is unresolved. We have data, we have timing, we have plausible mechanisms and uncomfortable correlations. What we don't have is proof, consensus, or a clear path forward. The scientific community hasn't rejected this. They haven't accepted it either. It exists in that liminal space where most anomalies live, acknowledged but not explained, recorded but not understood. What would count as evidence? More observations during future flybys. Controlled experiments showing that electromagnetic stimuli can excite Earth's resonant cavity modes at specific frequencies. Better modelling of ionospheric responses to solar wind disturbances. Blind predictions followed by confirmation. Science has tools for this. The question is whether anyone will use them, or whether this observation will join the long list of curiosities that get filed away and forgotten. Discomfort exists on all sides. Skeptics are uncomfortable because the timing is too good, and dismissing it feels like dodging. Proponents are uncomfortable because they can't prove the mechanism, and advocating too strongly invites ridicule. Everyone is uncomfortable because the null hypothesis, pure coincidence, requires believing that unrelated events aligned with precision that strains credulity. So we're stuck with a mystery that refuses to resolve cleanly. The mystery itself might be the point. Maybe we're not supposed to have answers yet. Maybe this is just Earth reminding us that it's more complex than our models, more dynamic than our instruments usually reveal, more connected to the cosmos than we give it credit for. And maybe, just maybe, we should pay attention when that connection becomes visible. Because if it happened twice, it might happen again. And next time, we'll be watching. Part 11. Interstellar objects are showing up. More often. Oumuamua arrived first in October of 2017, and nobody was ready for it. The object was already leaving the solar system when we spotted it, tumbling through space at a velocity that made its extrasolar origin undeniable. It accelerated away from the sun in a way that couldn't be explained by gravity alone, suggesting outgassing, even though no coma was visible. It was elongated, spinning, weird, and it was gone before we could get a good look. Borisov came next in August of 2019. This one looked more like a comet, with a visible coma and a trajectory that screamed, "Not from here." We had more time to study it. More telescopes pointed its way. More data collected. It behaved mostly as expected, following predictions for how a comet from another star system should look and act. Less controversial than Oumuamua, less dramatic, but still remarkable for being only the second confirmed interstellar visitor in human history. 3I Atlas is the third, and it arrived in 2025. The detection happened earlier in its approach, giving astronomers time to plan observations, to coordinate instruments, to track it through perigee and out again. It's smaller than Borisov, fainter than Oumuamua, but it's ours to watch. Or it was, for the brief window when it passed through our neighbourhood at 1.8 astronomical units, close enough to register on sensors that weren't even looking for it. Detection bias is massive in astronomy. We only see what our instruments are capable of detecting, and for most of history our instruments couldn't detect interstellar objects at all. They're small, dark, fast, and they don't stick around. Unless one happens to pass close. To Earth, while we're looking in the right direction with the right equipment, it might as well not exist. The fact that we've found 3 in 8 years doesn't mean 3 arrived. It means 3 arrived and we noticed. Survey improvements are changing that. Telescopes like Pan-STARRS and the Catalina Sky Survey are designed to find transient objects, to map the entire visible sky repeatedly, to catch things that move or change. As these systems improve, as sensitivity increases, as more telescopes come online, we're going to find more interstellar visitors. Not because they're arriving more frequently, because we're finally able to see them. Actual frequency remains unknown. Estimates suggest that interstellar objects pass through the inner solar system regularly, maybe 1 per year, maybe dozens per year, depending on assumptions about size distributions and velocities. Most pass unnoticed. A few get close enough to detect, and once in a while, one passes close enough that it becomes a headline instead of a footnote in an astronomical catalogue. Public reaction cycles through predictable phases. Initial excitement at the discovery. Speculation about composition, origin, trajectory. Brief flurries of UFO theories that get debunked or ignored. Then fading interest as the object leaves and the next news cycle begins. 3I Atlas followed this pattern exactly, generating interest when it was announced, peaking during closest approach, and then dropping off as it continued its journey back into interstellar space. Except this flyby drew attention for reasons beyond astronomy. The timing mattered. The electromagnetic anomaly mattered. People who'd never heard of Schumann resonances or earthquake precursors started paying attention because something happened that didn't fit the script. An interstellar visitor was supposed to be a passive event, something we observe from a distance without interaction. Instead, Earth lit up at 25 Hz 3 hours before perigee, and suddenly this wasn't just an astronomy story anymore. The connection is unproven, it might be meaningless, but the visibility is growing. More people are watching Schumann monitors now. More people are aware that Earth has an electromagnetic environment that can be measured and tracked. More people are asking whether cosmic events and terrestrial phenomena might be coupled in ways we haven't mapped. And that visibility, that awareness, might be more important than any single anomaly. Part 12. Earth's electromagnetic environment is getting louder. Solar cycle. 25 is ramping up, and the sun is getting active again. Solar flares, coronal mass ejections, high-speed solar wind streams, all increasing in frequency as the sun approaches its maximum. This is normal. This happens every 11 years or so as the solar magnetic field flips and reorganizes. But normal doesn't mean quiet. Normal means Earth's magnetosphere is getting hammered by charged particles and electromagnetic disturbances at rates we haven't seen since the last solar maximum. Geomagnetic disturbances follow solar activity. When a coronal mass ejection hits Earth's magnetosphere, it compresses the field, drives currents in the ionosphere, creates auroras at high latitudes. These disturbances show up in Schumann resonance data as broadband increases, as elevated background levels, as shifts in the dominant frequency peaks. The entire electromagnetic environment becomes noisier, more chaotic, harder to interpret. Monitoring sensitivity has increased dramatically over the past few decades. More stations, better instruments, higher data rates, online publication of results. We're watching Earth's electromagnetic environment more closely than ever before, which means we're catching anomalies that previous generations would have missed. Some of what looks like increased activity might just be increased visibility. We're not sure Earth is actually getting louder, or if we're just listening more carefully. Louder doesn't mean dangerous. Earth has survived billions of years of solar wind, geomagnetic storms, cosmic ray bombardment, and countless other electromagnetic insults. The atmosphere shields us. The magnetosphere deflects most of the incoming particles. Life exists because Earth is remarkably good at handling these disturbances without catastrophic consequences. So when we talk about the electromagnetic environment getting louder, we're not predicting doom, we're noting variability. Cumulative stress is a concept borrowed from materials science and engineering. When you stress a material repeatedly, even below its failure threshold, microscopic damage accumulates. Eventually the material fails at stresses it could have handled easily when it was fresh. The idea that Earth's crust might experience cumulative electromagnetic stress is speculative, but it's not incoherent. If piezoelectric effects are real, if electromagnetic coupling between the atmosphere and the crust exists, then repeated disturbances might matter, even if each individual event is small. Background versus spikes is a critical distinction. A high background level of electromagnetic noise is different from a sharp, isolated spike. Background is the hum of activity, the average state of the system. Spikes are departures from the average, moments when something unusual happens. The 25 Hz signal wasn't a change in background, it was a spike, a discrete event, standing out against the baseline in a way that demanded explanation. Schumann variability is well documented. The resonances shift slightly with solar activity, with seasonal changes in ionospheric height, with local thunderstorm activity. These variations are expected and explained. What's harder to explain are the isolated frequency spikes that appear and disappear without obvious triggers, the narrow band signals that don't fit the usual categories. These might be artifacts. They might be natural phenomena we haven't characterized. Or they might be indicators of processes we're only beginning to understand. Speculation boundaries need to be clear. We're talking about possibilities, not certainties. We're asking questions, not providing answers. The electromagnetic environment is complex, multiply-connected, sensitive to inputs we might not have identified yet. Saying it's getting louder is shorthand for saying it's getting more active, more variable, harder to predict. Whether that matters for seismic activity, for atmospheric phenomena, for anything beyond electromagnetic measurements themselves, remains an open question. Systemic complexity is the real challenge. Earth isn't a simple system, it's a coupled set of subsystems, each influencing the others in ways that create feedback loops, non-linear responses, emergent behaviours. The atmosphere affects the ionosphere. The ionosphere affects Schumann resonances. Solar activity affects everything, and maybe, just maybe, interstellar objects passing through the solar system add one more variable to an already complicated equation. Understanding that complexity requires tools we're only beginning to develop, and one of those tools is artificial intelligence. Part 13, AI is now mining anomalies. Humans ignored. AI scans massive data sets with patience humans don't have. Feed a neural network a decade of Schumann resonance spectrograms, and it'll find patterns you'd never notice by eye. Train it to recognize anomalies, and it'll flag signals that don't fit the usual categories, pulling them out of terabytes of data in hours instead of years. Machine learning doesn't get bored. It doesn't have biases about what's interesting. It just processes data and reports what it finds. Human attention is selective and limited. We look at spectrograms when we're interested, when something prompted us to check. We notice dramatic events, obvious spikes, changes that stand out visually. What we miss are the subtle anomalies, the borderline cases, the signals that sit just above the noise floor without being dramatic enough to catch our eye. AI doesn't have that limitation. It evaluates every data point with equal attention, finding needles in haystacks because it checks every piece of hay. Anomaly detection is different from prediction. AI isn't predicting earthquakes or forecasting electromagnetic events. It's identifying data points that don't match the training set, that fall outside the expected distribution, that represent statistical outliers. Some of these outliers are artifacts, some are interesting, and some might be indicators of processes we didn't know existed because we never looked for them systematically. AI finds boring signals. That's its superpower. Humans gravitate toward drama, toward obvious patterns, toward things that tell stories. AI finds the 3 standard deviation events that happen at 2 a.m. when nobody's watching, the frequency shifts that last 30 seconds, the correlations between parameters that humans wouldn't think to compare. These boring signals might be where the real discoveries hide, because they're the ones we've been systematically ignoring. Dismissed data is being re-evaluated. Old datasets that were analysed once and filed away are being fed to AI systems that weren't available when the data was first collected. Patterns are emerging that nobody saw the first time around. Correlations between electromagnetic anomalies and seismic events that seemed random when examined by eye start looking structured when AI examines thousands of examples. This doesn't prove causation, but it suggests relationships worth investigating. Risk state modelling is the goal. Instead of predicting specific events, AI might be able to estimate whether Earth's electromagnetic or seismic systems are in elevated risk states, periods when anomalies are more likely, when the probability of unusual events increases. This is probabilistic, not deterministic. It's weather forecasting for geophysics, giving likelihoods instead of certainties. And it might be the best we can do with complex chaotic systems. AI limitations are real and important. Neural networks are black boxes. They find patterns, but they don't explain why those patterns exist. An AI might flag every Schumann anomaly before major earthquakes and still not tell you what physical mechanism connects them. Correlation isn't causation, and AI is fundamentally a correlation-finding machine. Human scientists still need to build the explanatory models, design the experiments, figure out what the patterns mean. Future reinterpretation is inevitable. As AI tools improve, as datasets grow, as our understanding of Earth's electromagnetic environment deepens, we'll look back at signals we dismissed and see them differently. The 25 Hz spike at 0240 UTC might someday be recognised as a category of event we haven't named yet. Part of a pattern we didn't know existed because we never had the tools to see it. Or it might remain an isolated anomaly, interesting but unexplained, filed away with all the other mysteries. The 25 Hz mystery is exactly the kind of problem AI excels at. You have massive datasets, rare events, unclear patterns, and human observers who can't watch everything all the time. Train a network on Schumann data, teach it to recognize different types of anomalies, let it scan continuously for signals that match the 3i Atlas event. Maybe it finds nothing. Maybe it finds dozens of similar events scattered through the archives. Either way, you've answered a question that would take human researchers years to investigate manually. And that investigation is happening now, quietly, in labs and research groups that don't publicize preliminary results. Precursor science is coming back from the fringe, not with claims of prediction, but with better tools and more humility about what can and can't be known. Part 14. The return of precursor science from the fringe. Precursor research was sidelined because it promised too much and delivered too little. Every major earthquake in the 20th century was followed by claims that someone had detected warning signs days or weeks earlier. Radon emissions, animal behaviour, electromagnetic anomalies, groundwater changes. None of it produced reliable predictions. None of it saved lives. And after enough false alarms and missed events, the scientific community largely gave up on the idea that earthquakes telegraph their intentions. The stigma is real. Suggesting that you're working on earthquake precursors is professional suicide in seismology. You'll be associated with pseudoscience, with hucksters selling prediction systems that don't work, with the long history of failed attempts to beat the odds. So researchers who are interested in precursor phenomena keep their heads down, publish in obscure journals, avoid the word prediction, like it's radioactive. Data hasn't gone away. The observations that sparked precursor research in the first place are still there, still showing up in datasets, still begging for explanation. Electromagnetic anomalies before earthquakes, changes in groundwater chemistry, thermal infrared signatures. These correlations exist even if we can't use them for prediction, and ignoring them because they're inconvenient means we're missing opportunities to understand how Earth's crust behaves under stress. Modern framing is different. Nobody's claiming they can predict the exact time and location of earthquakes anymore. The goal is risk assessment, identifying periods when seismic systems are in elevated states, when the probability of rupture increases. This is a softer claim, less vulnerable to falsification, more compatible with the chaotic nature of earthquake physics. It's also more useful. Knowing that a fault system is stressed might not tell you when it'll fail, but it tells you to be more prepared. Multi-signal approaches are how modern precursor research operates. Instead of relying on a single indicator, researchers look at combinations of signals across different measurement types: electromagnetic, seismic, geodetic, chemical, thermal. The idea is that if multiple independent measurements show anomalies before events, the correlation becomes harder to dismiss as coincidence, and if you can characterize the pattern of anomalies, you might build models that estimate risk better than any single measurement could. 25 Hz fits into this debate perfectly. It's an electromagnetic anomaly at a frequency associated with crustal stress. It appeared before the Japan earthquake, and during an event that might have triggered stress in Earth systems. It's exactly the kind of signal precursor researchers look for, and exactly the kind of signal skeptics dismiss as post hoc pattern matching. Both sides are entrenched. Both sides have good reasons for their positions. No warning claims are being made, and that's critical. Nobody's saying the Tomsk data predicted the Japan earthquake or warned about anything 3i Atlas might have triggered. The observation is that anomalies appeared in temporal proximity to significant events, and that's worth investigating without claiming predictive power. Science can study correlations without asserting causation. In fact, that's how most discoveries start. Humility is required here more than anywhere else. The history of precursor science is a history of overconfidence, followed by failure. Researchers who claim they could predict earthquakes destroyed their own credibility when their predictions didn't pan out. The ones who survived are the ones who learned to phrase their findings carefully, to emphasize uncertainty, to admit when they don't know. That humility is how precursor science might eventually rejoin mainstream research. Funding and resistance are intertwined. Funding agencies don't want to support research that's associated with pseudoscience, or that seems unlikely to produce practical results. Precursor research struggles to get funded, which means it attracts fewer high-quality researchers, which means the work that does get done is often lower quality, which reinforces the perception that it's not worth funding. Breaking this cycle requires high-profile success or wealthy patrons willing to take risks. Slow re-entry into discourse is happening anyway. Papers on electromagnetic precursors are being published in respectable journals, carefully framed, heavily caveated, but present nonetheless. Conferences include sessions on multi-parameter monitoring. AI is finding patterns in data that humans dismissed. The stigma is fading slowly, not because anyone proved precursors work, but because enough researchers decided it's worth looking again with better tools. And all of this context, all of this history, comes crashing into focus when you look at what happened at 0240 UTC on December 19th, 2025. Because if that signal was real, if it was connected to the flyby or to seismic stress or to anything at all, then we just witnessed something that precursor researchers have been claiming for decades and skeptics have been denying. And maybe, just maybe, it's time to ask the question that ties everything together. Part 15. Did Earth just answer back? 0240 Coordinated Universal Time. 3 hours and 20 minutes before perigee. A single frequency spike at 25 Hz, isolated and narrow, appearing on a sensor in Russia, while an interstellar object completed a flyby that had been anticipated for months. This is where we started. And this is where we end, because the question hasn't been answered. It's only been expanded. Did Earth speak? That's metaphorical, obviously. Earth doesn't have intent. It doesn't have consciousness. It's a planet, a collection of physical systems following physical laws without purpose or awareness. But systems can respond without being aware. A bell rings when you strike it, not because it wants to, but because physics says it must. And maybe Earth rang at 25 Hz because something struck a resonant mode in its electromagnetic cavity, something that originated 1.8 astronomical units away. Unanswered questions surround us. We don't know if the signal was real or artifactual. We don't know if the timing was meaningful or coincidental. We don't know if similar events have happened before or if this was unique. We don't know what mechanism could couple an interstellar object at that distance to Earth's Schumann resonances. We don't know if the Japan earthquake anomaly was related or independent. We don't even know if asking these questions is productive or if we're chasing ghosts. Science owes the public transparency. When anomalies occur, when patterns appear, when observations don't fit existing models, the scientific community has a responsibility to acknowledge them instead of dismissing them reflexively. Not to sensationalize, not to claim explanations we don't have, but to say clearly that something happened, we noticed it, we're not sure what it means, and we're working on figuring it out. That honesty builds trust. Silence builds conspiracy theories. Dismissal isn't resolution. Saying it's probably nothing and moving on might be correct 99 times out of 100, but that 100th time is where discoveries live. Continental drift was dismissed. Heliocentrism was dismissed. Quantum mechanics was dismissed by Einstein himself. Being skeptical is essential, but being so skeptical that you refuse to investigate uncomfortable observations is how you miss revolutions in understanding. Listening matters more than believing. You don't have to accept that 3I Atlas triggered an electromagnetic response to take the observation seriously. You don't have to believe in earthquake precursors to study electromagnetic anomalies systematically. You don't have to commit to any particular explanation to acknowledge that Earth's electromagnetic environment is complex, dynamic, and capable of surprising us. Listening means paying attention. Believing means committing to an explanation. They're not the same thing. Transparency serves everyone. If Schumann anomalies turn out to be meaningless artifacts, the public deserves to know that and understand why. If they turn out to be indicators of real physical processes, the public deserves to know that too. What the public doesn't deserve is silence, dismissal, or condescension from experts who are uncomfortable discussing observations that don't fit their models. Science works best when it engages openly with anomalies instead of hiding them. This anomaly is an invitation. It's inviting us to look more carefully at how Earth responds to cosmic events. It's inviting us to build better models of electromagnetic coupling between the ionosphere, magnetosphere, and crust. It's inviting us to deploy better sensors, gather more data, apply AI tools to archived observations, and see if patterns emerge that we've been missing. And it's inviting us to be humble about what we think we know, because the universe has a habit of being stranger than our models predict. No conclusions exist yet, and that's fine. Science isn't about having all the answers immediately. It's about asking the right questions, gathering relevant data, testing hypotheses, and refining understanding over time. The 3I Atlas flyby and the 25 Hz anomaly raise questions we don't have answers to yet. Maybe future observations will resolve them. Maybe they'll deepen the mystery. Either way, we're better off asking than ignoring. Curiosity drives progress, not fear. Fear would say we shouldn't investigate this because it might lead to uncomfortable implications. Fear would say we should stick to established models and ignore anything that doesn't fit. Curiosity says the opposite. Curiosity says anomalies are interesting, patterns are worth exploring, and understanding deepens when we take observations seriously, regardless of whether they fit our expectations. And if Earth did answer back, if there was a response we detected at 0240 UTC, then curiosity demands we figure out what it meant. The universe spoke. Maybe Earth answered. And we, standing here with our sensors and our spectrograms and our incomplete understanding, have the privilege and responsibility of listening to both.